Good morning and welcome to Tech 240 on Wednesday, April 28th. Today is kind of a bittersweet day, at least for me, because it's the very last day of the class. So that is a little bit sad, at least for me, because I really enjoy this stuff. I really enjoy talking to you about electrical circuits and electrical machines because it's so important and applicable to our daily lives. If you really think about it, you use the electric grid and all the components and devices that plug into it an awful lot in your daily life. So things in this course really do explain a lot of what we do on a daily basis, a lot of the things that we use on a daily basis. So that's a little bit sad because it's coming to an end and I really did enjoy it. I hope that you enjoyed it as well, at least to some extent. And I hope you found it somewhat useful and somewhat interesting as well. But it is coming to an end, and it's not all a bad thing. Like I said, it's bittersweet. So the good news is we're heading into summer, and nobody's going to complain about that, including me. I enjoy summer as much as anyone else. I love being outside and going for bike rides and runs and being out on the lake. And all of that is really good stuff. And spending more time with the family, it's a good thing too. So it's a little bit bittersweet. So the purpose of this video is to talk about the last exam, exam 3. I don't really like to call it a final exam because it's not intended to be cumulative. I like to call it exam 3. That implies it's about the third portion of the semester. So we'll talk about that in just a minute, but let's review the schedule first. So first of all, we do have lab 19 due today. That's the lab about rectifiers. So that's due today by 11:55 p.m. And then the very last lab in the class, lab 20, that's about AC electricity in the sense of talking about power factor and real, reactive, and apparent power. Remember all the units for all of those. That's one of the trickier things. Lab 20 is due on Sunday, May 2nd by 11:55 p.m. So I tried to push that due date back pretty much as far as I could realistically do to give you as much time as you possibly could have to do that. But I still have to grade that and get those grades submitted and things. So lab 20 due on Sunday, May 2nd by 11:55 p.m. And the only other thing on the schedule is exam 3. So exam 3, you can see on the schedule, it says TBD. The day of the final exam is assigned by the registrar, and those dates don't come out until halfway through the semester. So those dates have come out, and if you look at your final exam schedule, what it will say is the final exam for Tech 240 is on Monday, May 3rd, from 3:10 to 5:10 p.m. But what I'm going to do is just a little bit different. I'm going to set it up very much like exam 1 and exam 2 in this class were. I don't see any reason to limit you to taking it on Monday from 3:10 to 5:10 p.m. So I'm going to have the exam open up at midnight on Monday, May 3rd. And then you'll have any 3-hour window that you want in that day, that 23 hours and 55 minutes. So pick a 3-hour window during which to take the exam 3, and then it will close at 11:55 p.m. that same day. So it'll open at midnight on Monday, May 3rd. It'll close at 11:55 p.m. also on Monday, May 3rd. The time limit will be 3 hours. So from the time you start, you will have 3 hours or 11:55 p.m., whichever comes first. So that being said, don't start the exam at 11 p.m. because then you've just shortened your window from 3 hours to 1 hour. So no reason to do that. So start the exam by 9 p.m. at the very latest. All right. So exam 3 is going to be on Monday of exam week, but you can take it anytime during that day that you want to. In a few minutes, I'll switch over to the document camera and we'll talk about the content of the exam. But first, a little bit more about the format and structure of the exam. It's going to be set up very much like the first and second exams in this class. So that's a good good reference point to use. Now you kind of know how I write exam questions and how I like to structure exams. There will definitely be some multiple choice and true false questions on exam 3, and there will definitely be some calculation problems on exam 3. I would estimate, I haven't set it up yet, so I can't tell you exactly, but I would estimate there will be a total of maybe between 50 to 60 questions, give or take 10 or so, something like that. That seems to be a good number, I think. And of those 50 to 60 questions, I would say probably about half of the points will come from multiple choice or true false type questions, qualitative type questions. And the other half of the points will come from the calculation questions. For calculation questions, the best way to study for that is to double check all of your labs, redo all of the labs. And you can also read through the lab manual again, because there are a lot of example problems just built into the lab manual, especially on the filters section. There are lots of example problems that are written right into the lab manual, and that's very intentional so that you can work those problems as well, and you can check your answers in the lab manual. In the back of the lab manual, I forget what page, but there's also a review section on capacitors and inductors, and the answer key is given in there in the back of the lab manual. So that's another thing that you can use to study for the calculation problems. The questions will come from a couple of different sources. They'll come from the lecture material and the slides that we talked through. They will come from the lab material, the written part of the lab manual. And they will also come from the labs themselves. The actual calculations will be similar, but not identical, similar to the lab problems that we've done in the last third of this class. So I'd recommend reviewing all of those things, reviewing the lecture slides, reviewing the lab manual, as well as the calculations that you did for the labs. I think that pretty well covers it. What resources do you want to have on hand? Well, you pretty much want to have those resources on hand. You probably want to have your lab manual right in front of you when you're taking the exam. You probably want to have your labs that you did right in front of you, so you can use those as resources. And you might want to have access to the videos. You can always go back and you can rewatch portions of the videos during the exam. I'm not stopping you from doing that. The only thing I don't want you to use, as I've said several times already, is each other. So you can't be texting or communicating with other people in the class. You need to do the exam independently by yourself. You also want to make sure that you have a calculator for this exam, because you're not going to want to be doing these calculations by hand. When you take and work with things like scientific notation, like 10 to the minus 6 farads, or 3 times 10 to the minus 3 henries, things like that, it's not convenient to be doing those calculations by hand. So make sure you have a calculator, and make sure that you know how to use scientific notation on that calculator. Because it's not a surprise, you're definitely going to be using scientific notation for the calculation problems on the exam. I'd also strongly recommend that you have a writing utensil and a piece of scratch paper, because I'd strongly recommend that you write out these problems and write out your calculations. If you try to do these calculations in your head, you're probably going to mess them up. I mean, I know I would. If I tried to do all these calculations in my head or keep track of what I'm doing in my head, then I would almost certainly make a mistake. So I'd strongly recommend that you write this down and do it step by step on your piece of scratch paper. You're going to have time for that. I don't think the 3-hour time limit is really going to be a major concern. And that was true in the first 2 exams too. I don't think hardly anybody used the full 3 hours in the first 2 exams. So the time shouldn't really be a major concern. So take your time and work slowly and write out the steps in your calculations step by step. That will minimize the possibility that you make a silly mistake. I know that's what I would do. I would definitely write them out step by step. All right, so that being said, we've talked about the materials that you want to have on hand when you're taking the exam. We've talked about the structure of the exam and the schedule for the exam. So I think all that's really left is to talk about the content of what's going to be on the exam. So to do that, I'm going to switch over to my document camera.
All right, let's talk about the topics that we've covered since exam 2 that are going to be on exam 3. Notice I'm calling it exam 3, not the final exam, because it just counts like exam 1 and exam 2 did. They're all equally weighted. So the first thing that we covered after exam 2 was capacitors, and you should know about their construction and their operation, basically their operating principles. Remember the mnemonic device ICE, where we said in a capacitor C, the current I leads voltage E. We also talked about capacitive reactance and what reactance is and how to calculate it. There's a formula here for capacitive reactance. We talked about impedance and what impedance is. And we did some simple AC circuit analysis, like finding the current flow in an AC circuit for RC series circuits. That is, when we have a resistor and a capacitor in series in an AC circuit, we can use our modified version of Ohm's law with V equals IX if it's purely capacitive, or V equals IZ if it's not purely capacitive. That was the first day after exam 2. And then in the next day, we talked about inductors. And we did a very analogous discussion of inductors compared to what we did for capacitors. They were very similar. So we talked about the construction and the operation of an inductor, how it works. And the mnemonic device for an inductor is Eli. So you put them together, and the mnemonic device is Eli the Iceman. Eli, the mnemonic device, has L in the middle, and L is the variable for inductance. And we have I, current, that comes after or lags E, voltage. So current lags voltage in an inductor. Then we talked about inductive reactance. And the formula for that, remember there was an equation to find inductive reactance. And once again, we talked about impedance. And we did some AC circuit analysis. For RL series circuits. Okay, once we had that in our back pocket, once we understood capacitors and inductors, then that enabled us to start talking about filters. And the first one that we talked about was the low-pass filter. The low-pass filter, what is its purpose? It's kind of self-explanatory with the name, but what is the purpose? The construction and operation, once again, construction and operation, how it works, and the circuit design. You should be able to design a circuit that is a low-pass filter, either an RC or an RL low-pass filter circuit. You should be able to design one. They're not too simple to construct. So we talked about RC and RL low-pass filters. And for both of those, for RC and RL low-pass filters, we talked about the cutoff frequency, and we talked about the voltage output, V out, for a given specified frequency. And it's going to vary depending on what the frequency is. your output voltage is going to vary depending on what the frequency of the input is. Then we did kind of the same thing with high-pass filters. Once we understood low-pass filters, high-pass filters were kind of a cakewalk. High-pass filters. So once again, we have the purpose of a high-pass filter, the construction, how it's put together, an operation, how it works. And once again, the circuit design, you should be able to design a high-pass filter circuit, either an RC or an RL high-pass filter. And once again, we talked about both of these. We talked about RC and RL high-pass filters. And for both of these, you should be able to calculate the cutoff frequency, F sub C. Yeah, we abbreviated that F sub C. And same thing as up here, you should be able to calculate the output voltage for a specified frequency. Of course, I'd have to give you the input voltage and frequency, and you should be able to calculate the output voltage. Okay, so that was high-pass filters. Then the next thing we talked about, I'll switch pages. The next thing was rectifiers and inverters. So the first thing we talked about kind of briefly was inverters. And we talked about how they operate. And we talked about a couple different types of inverters. So you should understand what inverters are and how they operate. And then we spent some time talking about rectifiers, and the lab was on rectifiers. And the first one that we talked about was the half-wave rectifier. This is the simplest one and probably the least useful, but it's important to understand this before we go on to the more complicated ones. So the half-wave rectifier, once again, the construction and operation, how it's put together and how it operates. Construction and operation of a half-wave rectifier. And also, what does the output waveform look like? You should know what the output waveform looks like for a half-wave rectifier. And then we talked about full-wave rectifiers. There are actually two different kinds of full-wave rectifiers that we talked about. The first one was the bridge rectifier. This is the one with 4 diodes arranged in a specific manner. Bridge rectifier. So for the bridge rectifier, once again, it's construction, how you put it together, and its operation, how it works. There's, I think, a pretty good description of its operation in the lab manual. So make sure you read through that and understand how this works in both the positive and the negative half cycles. The current flow is not going through the same path in the positive half cycle as it is in the negative half cycle. So you should understand how this bridge rectifier works. And same thing up here, the output waveform, same thing as up here. So for a bridge rectifier, you should know what the output waveform looks like. And the other type of full wave rectifier that we talked about was called the center tap rectifier. And that was basically the combination of a rectifier and a transformer. So that one had the advantage that you could change the output voltage by changing the turns ratio in the transformer portion of the rectifier. So same thing, the construction, how it's put together and how it operates, the principles by which it operates, and the output waveform. The output waveform for this one, it's a full wave rectifier just like this one is, so they're going to have very similar output waveforms. The only real difference here is that this one has an incorporated transformer, and so the output voltage could be different for this one than it was from this one, because this one had a transformer built into it. All right, and the last thing we talked about relevant to rectifiers was the output smoothing capacitor. Because we noticed that the output waveforms from all of these weren't really DC, and we're trying to get something that is as close to DC as possible. And the easiest way to do this is by incorporating an output smoothing capacitor at the output of the rectifier. So I want you to know what it is and how it works. What it's doing, how it's smoothing the output of the rectifier circuit. All right, that was it for rectifiers and inverters. The last thing we talked about in the previous class was RMS voltage and power factor. And there were a few other things that we had to define first before we could understand what power factor was. The first thing was RMS voltage. So I'm not going to ask you to derive it. Remember, we actually kind of derived it in the presentation last time, but I'm not going to ask you to derive it. I'm just going to ask you to know what it is and how to do some calculations with it. So what it is, you should definitely know the definition of what it is and how to use it. It's pretty simple to use. Whenever we have an equation that includes voltage for AC circuits, you just have to plug in the root mean square voltage, not the peak voltage. But you do need to know how to convert from root mean square voltage back and forth to peak voltage, back and forth to peak. All right, so if you know any one of these, and you know it's a sinusoid wave, which you can assume for AC circuits, it's a sine wave, then you should be able to convert from one to another between root mean square voltage and peak to peak voltage of the waveform. And the last thing that we talked about was power factor. But in order to really understand that, we had to define a few other terms. So we had to define what real power is, and remember the variable for real power is R, and the units are watts. And we also had to define what reactive power is, and the variable for reactive power is Q, and the units are var. Or it could be kilowatts and kilovar, or megawatts and megavar, and so on and so forth. And the last thing that we had to define here for different kinds of power is called apparent power, which is the power that actually has to be provided by the utility. And the variable that we used here was S. That's the standard variable for apparent power. And the units are volt amps, or kilovolt amps, megavolt amps, gigavolt amps, and so forth. Remember your power triangle. This is called a power triangle. This is pretty ubiquitous in the electric industry, where you have your vector summations. So this vector here is the real power R, measured in watts. This vector vertically here is the reactive power Q in var. And this vector here is the resulting vector from the sum of the real power and the reactive power, and this is the apparent power, S, in volt amps. The other important thing here is to note that this is the phase angle, And the phase angle is the difference between the current waveform and the voltage waveform. So this is the angle by which current leads voltage in the case of a capacitive circuit, or the angle by which current lags voltage in the case of an inductive circuit. A circuit that is, on the whole, has a net inductive property. More inductiveness than capacitiveness, if you will. All right, so that's the phase angle. And that helps because now you can use your trigonometric functions. Remember SOHCAHTOA, I mentioned that last time. I don't think I wrote it out last time, but here's what that looks like, just in case you don't remember from math class. SOHCAHTOA, the sine of any angle is equal to the opposite side length divided by the hypotenuse. The cosine of any angle is equal to the adjacent side length divided by the hypotenuse. And the tangent of any angle is equal to the opposite side length divided by the adjacent side length. So we have our phase angle, and since we know that angle, or we can find that angle, that allows us to do some of these trigonometric operations and find other values, like how much reactive power is necessary, or how much apparent power is necessary or being provided, things like that. The power factor then, that's what we're trying to get to. The power factor you can think of as a measure of efficiency of the electric grid or of a load being powered by the electric grid. And it is equal to cosine theta. Theta is the phase angle right there. That's one definition of power factor. And we have another definition because we know what cosine of any angle is. The cosine of any angle is equal to the adjacent side length divided by the hypotenuse. Here's our angle. The adjacent side length is r, and the hypotenuse is s. So the power factor is equal to cosine theta, which is equal to r divided by s, which is the real power in watts divided by the apparent power in voltamps. So it's kind of a measure of efficiency because it's telling you how much of the energy is actually being dissipated or consumed compared to how much power actually had to be provided by the utility company. So how much of the power that's being provided is actually being used or consumed or dissipated. That's why it's kind of a measure of efficiency. All right, so that's pretty much it for the main topics since exam 2.
And that pretty much wraps up the semester. So I want to close by saying thank you. Thank you for being a good class and attentive and participating in the class. I really enjoy teaching this class. I have enjoyed teaching all of you. I enjoy the material, and I also enjoy interacting with all of you. So it's been a fun semester. I hope you've gotten some enjoyment out of it as well. I recognize that not all parts are fun, but hopefully you've gotten some enjoyment and you've also learned something out of this class. That's my hope. I also wanted to say good luck to those of you that are graduating this semester. I wish you the best of luck in your job search and in your future career. And I also wanted to say, don't be a stranger. Come back to Turner Hall and keep us in the loop with how things are going and what you're up to. If you're not graduating this spring semester, then I hope to see you back in the fall semester, maybe in a different class that I'll have you as a student in, or maybe just in the hallways. Hopefully in the fall, we'll be back to a pretty normal set of circumstances, and we can actually, be walking down the hallway and see each other and say hello, things like that. So hoping for a normal fall semester. And I think we are. I think we're on track for a normal fall semester. So that's about it. I wish you all the best. Have a wonderful and safe summer break, and I hope to see you again soon. Have a good one.